Hi friends, this is Edwin Raj, a professor of mechanical engineering, St. Xavier's Catholic College of Engineering, Nagarkoil. Hope to meet you now through this medium. Because of this COVID-19, there was a break for college, and I hope you are all safe in home and keeping your family members safe. Since it is a long break, it is better to recollect what we have studied in thermal engineering course, thermal engineering 1. So it is not the entire course. I would just like to review what we have learned so far in this semester. Hope you are all studying. This is a God-given opportunity for you. A lot of time is provided to you so that you can study well and perform well when the exams come. We don't know exactly when the exams will be conducted. And you know that this is a continuation of thermodynamics. It is a professional core course. And before that, if you look at our vision and mission of our mechanical engineering department, basically we wanted to develop sound mechanical engineers so that only you can serve with excellence and innovation. So in order to achieve that vision, the first mission is we should have a clear conceptual understanding of the basic courses, and this thermal engineering is one of the basic core course. It's a continuation of thermodynamics. I understand you had a tough time in grasping the concept of thermodynamics. I hope this will reinforce your thinking. As far as this course is concerned, I can see the description. It says it's an application of fundamental of thermodynamics for analysis purposes. So it is, as I told earlier, this is a continuation of thermodynamics. So as an outcome, you can apply the thermodynamic concepts for various applications such as like gas power plants, vapor power plants, compressors, ice engines, turbines, like that. So you will get the ability to apply the fundamental concepts for analysis purpose. That's the objective and outcome of this course. Coming to the first unit of this thermal engineering, it is gas and steam power cycles. So in the word itself, we can understand that it is a power cycle. You can understand it is a power cycle. So it produces power. Power is rate of work. Work is, we can say that it is a mechanical energy, sharp rotation. So that is what power. There are two things two ways or two medium in which we can obtain power is through gas and through steam. So the first part of this first unit, it talks about the gas power cycle. Of course, we can still further divide it into air standard cycles. That's what we will be looking today, or in this first part of this lecture. And the second part of the first unit is the working fluid changes to steam. That's all. And fortunately, we have studied Rankine, reheat, and regenerative in thermodynamics also. So that portion we can do it in a hurried way. Coming to this air standard cycles, the basic of course goes to this most efficient cycle. It's an assumption. It's an ideal cycle. It is better to have that way, but there are a lot of practical difficulties in implementing Carnot cycle. So Carnot cycle, just if you review it, it has 4 reversible processes. You know that when it is reversible, it is very tough. Okay, but it is easy to remember this Carnot cycle as in a TS diagram, temperature entropy diagram. Entropy diagram, it looks like a square. So it is easy to always remember Carnot cycle because that is a base, that is the best we can achieve. That's an ideal cycle for all power cycles. So there we have, as I mentioned, 4 processes: isothermal heat addition. Isothermal means constant temperature heat addition. You can see from 1 to 2. You can see from 1 to 2. And it is horizontal in a TH diagram. That means T1 equal to T2. That is how. And then the second process is expansion, where we will get work. It is expanding, and it is isentropic. It is otherwise called as reversible adiabatic. That means isentropic means entropy is constant. That is why in process 2 to 3, you can see that in 2 to 3, S equal to constant. That means S2 is equal to S3. That you can see that it's a vertical line. So you can see that S2 is equal to S3. And the third process is, of course, it is isothermal. The word isothermal means it is temperature is constant. So T3 is equal to T4, and it's a horizontal line. Then to close the cycle, we have isentropic compression. That is, again, you can see that it is from 4 to 1 is isentropic compression. So it is entropy is constant. So you can say S4 is equal to S1. So of course, thermal efficiency is concerned. We always remember that output by input is efficiency. And when it comes to Carnot, the simplified form is 1 minus TEL is the low temperature divided by TH is the high temperature. So we can understand that way. So it is if this term, this TL by TH is small, the efficiency will be high. For this term to be very small, either the high temperature of heat addition should be high, or the temperature of heat rejection should be low. You can understand, higher the temperature of heat addition, higher the efficiency. Lower the temperature of heat rejection, better the efficiency. So high temperature is decided by the material property, the material which we use for power generation, how much temperature it can withstand. That decides the high temperature, and low temperature is where we reject the heat. This is all the basic of thermodynamics you would have already studied, so I'll just keep moving. So when it comes to air standard cycles, basically we assume air is a working fluid. As you know that air cannot be a working fluid for analysis purposes, theoretical analysis purposes, not the actual. Theoretical analysis of IC engines, internal combustion engines, to derive theoretical equations, how the performance of engine varies. For that, we assume air standard cycles. So you can see that in the actual case, actual IC engines, we supply air as well as fuel. Fuel may be either petrol or diesel or a gaseous fuel. Okay, so you have to supply air as well as fuel, which is supplied to the combustion chamber, and it generates a lot of heat, and it expands, producing power, and the combustion product has to be thrown out to the atmosphere for taking the fresh air and fuel for the next cycle. This is the actual case. But our standard assumption is we take only air, we are eliminating the fuel, and we are adding heat. Instead of combustion, we say that we are adding heat and air goes back. So this is ideal in the sense, this is our assumption for air standard cycles. So instead of actual air and fuel, we take only air. Instead of combustion, we take, say, heat addition. And let's see how it is. So the basic for assumption is we assume that working fluid is only air instead of air plus fuel. And we assume that the air behaves as an ideal gas. That is why we can apply gas laws. And again, we assume all the processes involved are reversible processes. You know how difficult to have a reversible process. Quasi-static process is a reversible process. No friction process is a reversible process. But we assume it as a reversible process. As I told in the previous slide, the combustion process is replaced with heat addition, and the exhaust process is replaced by heat rejection. Just to get a grip of it, we talk about the reciprocating engines or IC engines. You know that major components is an intake valve and exhaust valve, and you have a cylinder and a piston where the piston can move up and down. This piston can move up and down. And the linear movement of piston from bottom dead center to top dead center, we call it as a stroke length, stroke in short. The diameter of the cylinder or the piston both can be called as a bore diameter. In short, they call it as a bore, or the diameter of the piston or the diameter of the cylinder. You can look at this diagram. Here you can see that as the piston moves from TDC to BDC or BDC to TDC, that volume is called as the displacement volume, which we know how to calculate its cross-section area of the piston into the length of stroke. We say it is pi by 4 d square into L. And you can see another term, but also it is better to get familiarized with it, is clearance volume. That is the piston when it has reached the top dead center, still there is a gap to accommodate the compressed air fuel mixture, as well as the parts of the valves and other things. So that volume we call it as the clearance volume. These are the basic nomenclatures of ICs. So Otto cycle, let us say Otto cycle, or we'll call it as a gasoline cycle, or we say petrol engine, which is otherwise called as spark ignition engine, because the ignition, the combustion is ignited, started by giving a spark. That is why we call it as a spark ignition engine. Let us assume it is a 4-stroke SI engine. In 4-stroke SI engine, the top part is actual case, and the bottom diagram talks about the ideal one. This is ideal and this is the actual. Okay, how it starts? Let us see the actual first, then we'll come back to the ideal Otto cycle. So you can see that air and fuel is taken into the cylinder, and the piston moves upwards from bottom dead center to top dead center. Both the valves are closed. Both are closed here. Both are closed here. And the air fuel mixture will get compressed. Once it is compressed fully, you can see that a spark is given by the spark plug. Combustion starts. Expansion of air fuel takes place. It pushes the piston downwards. That is what we call it as a power stroke. Power or expansion stroke. Piston moves from top dead center to bottom dead center. So that is what we call it as a power or a expansion. You can see that here. Okay, expansion. So initially we are compressing, we are giving work to compress it. Then we combust it, burn it, then expand it. And you can see that the remaining is the exhaust. We throw off all the burn gases to the atmosphere, and the next cycle begins with the suction of air fuel. So this is approximated, assumed. You can see that intake and exhaust can be cancelled because almost it is just opposite direction. It is there. Intake is here. Intake is this direction, and exhaust is in this direction, so we can cancel it. So the remaining things, as an ideal case, we are doing as isentropic compression. Compression is isentropic. Isentropic means entropy constant. Then you can see that it's a PV diagram. It's vertical. So you can see that when it is a vertical diagram, constant volume heat addition. Constant volume heat addition. That is at TDC itself. At TDC itself. Instantaneously, heat is added to the air. Then you can see that it is a power stroke expansion. That is isentropic. Then we will throw off the heat to the atmosphere. That is here. That is at constant volume. That is when the piston is at bottom dead center. So that is how we draw the PV diagram. So it is an isentropic. You can see that it is vertical constant volume. So this Otto cycle is otherwise called as a constant volume cycle, because constant volume heat addition. Remember that, constant volume heat addition. So always remember this PV diagram, which is very important. You should be able to draw this PV diagram. Keep drawing PV diagram and remember it. How are you? Okay? Shall I keep going? Thank you. So Otto cycle diagram, this diagram you should be able to draw it and you should remember it. Especially this PV diagram is very, very important diagram. Very, very important diagram. So here only we understand it is a constant volume heat addition 2 to 3. This is the one gives the name constant volume heat addition process expansion. So constant volume is 2 to 3 here. Okay. So we can see that V2 is equal to V3. V2 is equal to V3. That is why we call it as a constant volume process. Here you can see that it is V4 is equal to V1. That is here, constant volume heat rejection. Here you can see that it is 1 to 2 is isentropic, that is S1, that is not needed of course, but remember it is S1 is equal to S2, and here you can see that S3 is equal to S4. Okay, this is what our PV and TS diagram of Otto cycle is all about. So Otto cycle derivation is very important, very, very important. They can ask into the exams. So please recollect and study that one. Okay, so I'm not doing it here as a revision. So the final equation comes as efficiency of Otto cycle is 1 minus 1 by Rk to the power gamma minus 1. And Rk is compression ratio. Compression ratio is equal to initial volume by final volume. It is final volume. So in other ways we put it as V1 by V2. We say that way, V1 by V2. Initial volume of the cylinder divided by the clearance volume left after the end of compression. So from this equation again you can see, understand that this is very important. This term should be lower to have maximum efficiency. So in order to have this a low value, that is 100 minus something, to a low value, the denominator Rk should be a high value. So higher the value of Rk, higher will be the efficiency. If Rk is higher, the efficiency will be higher. That is a concept. Of course, gamma is the ratio to specific heat. So this is what we understand from the derivations. Efficiency depends upon compression ratio, and you understand the higher the compression ratio, higher the efficiency. But that has a limits. So that is a theory portion in this unit. They can ask it. So you say that higher the compression ratio, higher the efficiency. So can we keep on increasing the compression ratio? That is a question comes into mind. We wanted to improve the efficiency, so let us keep on increasing the compression ratio. And you know that Otto cycle compression ratios are low, around 8 to 12, whereas in case of diesel engine, because that is a compression ignition engine, that is around 20 to 24, it is so high. So coming to this Otto cycle, the curve shows it will not keep on increasing. At a particular point, it goes down 5, and the optimum they say it is 8 or 10 or something like that. Why? You can see that we take air fuel mixture in the compression stroke actual case. If you take air and fuel together and compress it, the temperature will rise. And if the temperature rises above auto ignition temperature, automatically the fuel gets ignited, not in our hands. Normally we ignite the fuel by giving a spark at an appropriate time. If the temperature goes high, it burns automatically, early, rapidly, and it creates a lot of noise. Audible noise. It backfires. The piston, instead of moving forward, it can return back. It will put more load for the compression stroke. So that is called as knocking, or we call it as auto ignition, detonation. So abnormal combustion, different words. It is normal combustion. It's not normal combustion, it's an abnormal combustion. So auto ignition is not allowed. Auto ignition cannot be tolerated because it hurts the performance and causes engine damage. So there is an upper limit for compression stroke. You cannot keep on increasing. That is why the compression ratio for petrol engine is low. It's not about 10 or like that. It is not increased as we like. So another term also I wanted to introduce, I'm not going to explain much on it. So it is a mean effective pressure. You know that the pressure varies from here to here during the cycle. But we are going to, when the word mean is average, and the pressure keeps on varying here and here. But we try to put an average. This is average, or we call it as a mean effective pressure. So if this mean effective pressure is, it's a fictitious pressure. It is an assumed pressure. Fictitious means not real, but we assume. If the pressure is constant like that, the amount of work produced, work net, will be the same if the pressure is maintained constant. So that pressure is called as a mean effective pressure. If you know the mean effective pressure, then you can find out the work net as the swept volume multiplied by the swept volume, or displacement volume or swept volume. If you know the mean effective pressure into the swept volume, it will give the work net. So that is a word about the mean effective pressure, which can be used to compare the performance of different engines. So larger the mean effective pressure, more work we can obtain in a cycle and better the performance. That is how they evaluate. Coming to the next cycle, we have some set of problems to be done in auto cycle also. Then there is a diesel cycle. Diesel is, you know that the major difference between the auto cycle and the diesel is, always remember in auto cycle, this is auto, that is gasoline. Gasoline is petrol, auto, okay. So here you can see that air fuel mixture is compressed. Air fuel mixture is compressed. That is a major difference. And you have a spark plug. To start the combustion. When it comes to diesel engine, only air is, this is in actual case also, only air is compressed and fuel is injected. You don't add compress air plus fuel. So the problem of auto ignition is not there in diesel. There is no problem of auto ignition because we take only air. You can compress it as much as possible. If the engine can withstand, if the cylinder, piston, other things can withstand, you can compress it as much as possible. So because you are compressing only air, there is no issue of auto ignition, knocking or detonation in diesel engine, because you are adding the fuel at the later stage. That is a major difference. So fuel injection has a period, there is a duration. There is a duration, I'll put it that way. It has a duration. Whereas in Otto cycle we say instant combustion, instantaneously. That is why we say it is a constant volume. So here it comes. So you have as I told, you have a period of fuel injection, 2 to 3. That is why the only difference between the Otto cycle and diesel cycle, theoretically, if you look at the PV diagram, you can see that 2 to 3 is flat, horizontal line, not a vertical line. Vertical line is constant volume. This is a flat line. Flat means you can understand that pressure is constant. P2 is equal to P3. P2 is equal to P3. So it is a constant pressure heat addition. Constant pressure heat addition. As there is a duration of fuel injection, not instantaneous as we see it in Otto cycle or the petrol engine. So the similar diagrams you can see TS diagram, P is constant, and other things remains the same. 1 to 2 is isentropic, entropy is constant. 3 to 4 is again isentropic, where entropy is constant. Only difference is 2 to 3 is constant pressure. Of course, heat rejection 4 to 1 is again a constant volume process as we have it in Otto cycle. So here when you compress, as I told earlier, you can have a higher compression ratio, and it has a longer period, so it is possible to have constant pressure heat addition. So this cycle, diesel cycle, is otherwise called as constant pressure cycle. That is called as a constant volume cycle. That is called as a constant volume cycle. This can be called as a constant pressure cycle because the heat addition is at constant pressure. That is called as constant volume or Otto, because you know that heat addition takes place at constant volume. Here it is constant pressure. That difference you should always remember, because when you take the derivations, when you do the problems, you have to be very careful. Heat addition is constant pressure. Dual cycle is, dual means two. It's a combination of Otto and diesel. Why we do it? That is a better approximation for the actual case. Better approximating in a better way the combustion process. So you have better, it starts with constant volume, then you have a constant pressure. So it is both the constant volume and constant pressure heat addition. That is quite realistic. That is coming closer to the actual case. So this is a diesel cycle or a gasoline cycle. It can be used, but it is called as a dual cycle. So it is a combination of constant pressure and constant volume. You can see that we have put it like this. So you can see that 2 to x is constant volume, x to 3 is constant pressure. If you put 2 to 3 as heat addition is both constant volume and constant pressure. That is the difference between the diesel and the dual. I hope you understand the three air standard cycles. Otto is constant volume, diesel is constant pressure, and dual is, it's a combination of constant volume and constant pressure. In the next video or next PowerPoint, I would like to solve problems in Otto, diesel and dual. For you to understand that, I will do it. Thank you for listening. Have a nice day. Be a student always. I always tell it in your class, and I wanted to tell it again. Student is one who studies. There is no other definition. I hope you are studying well and do well in the coming exams. God bless you. Thank you.